Kp. All right, and we'll do some review of some gas stuff at the same time. So Kp is just an equilibrium constant, but instead of using concentrations, we use partial pressures. Please describe to your neighbor what a partial pressure is. Partial pressure. The pressure that an individual gas contributes to the total pressure. Now, if you only have one gas, then the partial pressure is the same as the overall pressure. So it's basically just the pressure of one individual gas. And if there's a mixture, and say it's a 50-50 mixture, then half of the total pressure will be the partial pressure of gas A, and the other half will be the pressure of gas B. So when we're doing Kp, we take, rather than the concentrations, we take the pressure of gas C and the pressure of gas D and divide by the pressure of gas A and the pressure of gas B. So it looks pretty much like our regular equilibrium equation with our coefficients up there. All right, and if these were the four gases that we had, then the total pressure, P total, would equal PA plus PB plus PC plus PD. Is good? How many of you remember the word mole fraction? Anybody? Okay. Let's say that we had 10 moles of A. And say we had 50 moles of gas in total. Mole fraction is as simple as so the mole fraction of A would simply be 10 moles of A divided by 50 moles of total gas, which would give you either 1/5 or 0.2. You can write a mole fraction as a fraction, or you can write it as a decimal. Does that make sense? Like it's not a complicated concept. And the symbol that we use for mole fraction is a capital letter X. In order to distinguish it from anything else, I usually put little crossbars on the top and the bottom of it. We don't have to write it very often. So if you want the mole fraction of A, that is how we would represent it. Yes? Now, if you know, like let's say that in our little example over here, if the total pressure is 3 atmospheres, that's for our 50 moles of gas. What would the pressure due to only gas A be? Yeah, 0.6, because what we have 1/5 of that pressure is due to gas A, right? So you could either write it as 1/5 of 3 atmospheres, or you could write it as 0.2 times 3 atmospheres, which gives you 0.6 atmospheres. Is good? Is easy? Okay, so really nothing complicated about it. So just refreshing your memory that that's what mole fraction means, and we can use it to calculate the partial pressure of a particular gas if we know the mole fraction. So that formula is given here. The pressure of gas A is equal to the mole fraction of gas A times the total pressure. And the formula for the mole fraction of A is moles of A over the total moles of gas. Okay. And I forgot this in my other class, but the mole fraction, just because we might as well, mole fraction of A is also equal to the partial pressure of A divided by the total pressure of A, because moles and pressure are related. Yes, they are proportional to one another. So the relationship between them will be the same. As moles go up, pressure goes up. As moles go down, pressure goes down. So the ratio between the two will be the same. Now, in Kp, hopefully it should be fairly obvious that if we have a solid or we have a liquid, should we include them in a Kp? Do liquids and solids have pressures? No. Okay. So do not include in Kp. And I don't know why I did not mention it here. Also, do not include aqueous, because aqueous don't have pressures either. So if we have this particular question here, our product has 4 H2 gas, so that's going to be the pressure of H2 raised to the 4. We have 4 H2O gas, which is H2O raised to the 4. All right, and that's it. So several things you might be asked to do using Kp. Given all the partial pressures, you might be asked to calculate Kp. Given some of the partial pressures, you might be asked to calculate Kp. Given moles of each gas at equilibrium and a volume of a container, well, do you even need volume? No, you don't. And you might be asked to calculate Kp, and you might be asked to calculate total pressures from Kp and moles of H gas, and you might be asked to calculate Kp from percentage dissociation. So those are 5 different types of calculations. And guess how many examples we have? 5. So we're going to go through them fairly quickly. especially the first ones. At equilibrium, it is found that the pressure of N2 is 0.94. So there's our pressure of N2. Our pressure of H2 is 0.39. Oh, and we are told we are already at equilibrium. Do we need a Rice table if we are at equilibrium? No. Okay. So there's our H2. And then our NH3. There we go. Toss them all in, raise them to the correct powers, and you get your final answer. Simple? Yes. Example 2, at equilibrium. In the following reaction at 303 Kelvin, the total pressure is 0.016 atmospheres, while the partial pressure of H2 was found to be 0.013 atmospheres. What is Kp for the reaction? So we have two gases here. We've got H2 and we have H2O. Those are the only two gases. In order to do Kp, we would need the pressure of water. How would we do that? Yeah, P total minus pH2 is equal to the pressure of water. So that would be 0.003 atmospheres. That looks like a B. You're right, that was 13. There we go. Okay, that's written over here. And then we just toss it into Kp and we get our final answer, which has only one sig fig because this right here has only one sig fig. An equilibrium mixture contains 2 moles of SO2, 1 mole of oxygen, and 6 moles of SO3. The total pressure is 54 kilopascals. Calculate Kp. Well, first of all, for this reaction, if we were to write Kp for this, Kp would be equal to, who goes on the top? SO3. So we've got pressure of SO3, and that's going to be squared. You can put it in brackets or not. It doesn't really matter. And then on the bottom, we're going to have pressure of SO2 squared and pressure of O2. Do we know these pressures yet? No. What do we know about those three substances? We know the moles. Can we go from knowing the moles to knowing the pressures? Because we also know our total pressure. And if we know the moles of each one, we also know the total moles of gas. So what could we now find? We can find the partial pressures, but before we find the partial pressures, we need to find the mole fraction. You can actually do it all at the same time if you want to, or you can do it separately. So in this particular case, I've written out the mole fractions separately, but you don't have to. You could take this part where you're calculating the moles of SO2, and you could pop it in right here. Does that make sense? if you wanted to. So you could just do it all in one step. Up to you. And for all of them, we have 1/9 is our fraction here. We have 6/9 is our fraction for our SO3. For all of them, the P total is the same, 54 kilopascals. And so we have partial pressure of SO2, partial pressure of O2, and partial pressure of SO3. And we just chuck those into our Kp, and we get 2. How are we feeling so far? Thumbs up, thumbs down, thumbs in the middle. Thumbs up, thumbs up. Okay, excellent. Let's keep going. All right. We are told that Kp is 3.72 atmosphere. What? Why is there atmospheres there? That should be gone. Okay. Fix. Because Kp has no unit. What pressure must be applied? What pressure must be applied to obtain a mixture containing 2 moles of CO, 1 mole of H2, and 4 moles of H2O? Now, when it asks what pressure must be applied, what pressure are we talking about there? Sorry? Atmospheric pressure? If we're talking about what pressure must be applied, that doesn't necessarily mean that it's going to be atmospheric pressure. We could apply more pressure or less pressure in order to get our equilibrium mixture to contain exactly those numbers of moles. Yeah? So basically we've got a container, yes, and we've got a pressure gauge on it, and we need to know whether we need to squish the container or expand the container. What is the little pressure gauge going to read? So that's going to be our total pressure. Okay. So we are wondering what that is. We're like, I don't know. Okay. What we do know, though, is that our total moles is 7 moles. And if we know our individual moles and our 7 moles, what can we calculate? We can use this to find mole fraction of each gas. All right. So in this case, I did not do it separately. In this case, I wrote it in. Here's our CO. Okay, here's our H2O, or sorry, our H2 mole fraction. And then here is our water mole fraction. And in each case, we are multiplying that mole fraction by the total pressure. But the total pressure, remember, that is our unknown. So we're just going to leave it as P total, or P tot. And then we can take those values. You could leave them as fractions, but I've chosen to make them, you know, you've got your 0.287, you got your 0.0, or sorry, why are you not moving? Thank you. 0.149, and you got your 0.5714. And we can take those three values here, here, and here, and those are our partial pressures. And we're going to chuck them into this formula for Kp. Okay, so we take our 0.2857 times P total, and we take our 0.1429 times P total, and we take our 0.5714 times P total. And right now that would suck because so far we've got a variable there, and we've got P total as a variable. But Kp was actually given to us in the question, so that's not an unknown, so we can throw that in there. Two of our P totals cancel out because it's all multiplication, and we're left with only one P total. And so we just do the algebra and solve for the total pressure, and we get 52 atmospheres. Okay, so it's just really just playing around with the numbers and getting to where you need to go. Yeah? Okay, this one has, and this is a dissociation, but not in the sense that we usually mean dissociation. Usually for dissociation, we are talking about ions, an ionic compound dissociating in water. In this case, we're not talking about that. We're talking about N2O4, one molecule, splitting into two NO2s, two molecules. And I guess I should have written that these things are gases. Fix. Now, we are told that at a pressure of 1.50 atmospheres, we have a flask that contains dinitrogen tetroxide. The gas is found to have dissociated by 20% at 298 Kelvin, as shown. So, what is the value of the equilibrium constant Kp? Well, if we assume that we start with 1 mole of N2O4, then we can do a Rice table. So we started with 1 mole of N2O4. What is 20% of 1? 0.2. So how much of it dissociated? 20%. So we're going to take away 0.2 moles, and we end up with 0.8 moles. We started with no NO2, and because this has a coefficient of 2, we need to multiply our change by 2. So instead of 0.2, it's going to be 0.4. So this ends up being 0.4. And that means our total moles of gas is 0.8 plus 0.4, which is 1.2 moles. We could have started with any number. Our mole fractions will end up the same. Okay? We could have started with any number of moles, so you can just assume whichever one you want. 1 happens to be a nice easy number. So our total moles of gas is 1.2. Now we have moles of N2O4, and we have moles of NO2, and we have the total gas moles. What can we find? We can find the mole fractions. Now, I got a question for you guys. I asked this to first period as well. This one has everything like written out, and we're just kind of like going through, and I'm like, writing a few things and highlighting a few things. Some of our other things just have like the question, and then there's blank, and then we write. Do you prefer the written out version, or do you prefer the blank version? Yeah. You like blank? How many people like blank? Okay. How many people like written out version? That's about what it was in the other class as well. Okay, so I'm going to, in the future, make it more blank than written out. Okay. We get what we get this year because there it is, but I'm going to make it more blank. Yeah. Okay. I think one of the reasons I made it written out is so that if you were away, you could get caught up in it, but you can always look at the answer key or whatever too. It'll just make the answer key bigger because we need a bigger answer key. Okay, anyway, we got our mole fractions here. Could you calculate your partial pressures before we turn the page? Let's do it. And then once you have your partial pressures, which you should get 1 and 0.5, yes, then you can just throw them into your KP and you get an answer. And I don't think my sig figs are correct here, so just ignore them for this question, okay? Just ignore sig figs here. All right, what I did with the other class is I gave them time to work on these exercises, or, you could also work on anything from 2.6 that you haven't done yet, any of those Gibbs free energy things, or anything from 2.5a that you haven't worked on. So anything from 2.5 or 2.6 that you haven't done, you can work on now. I also had a few people decide they wanted to work on the overall review for the unit. I'm going to leave that up to you. Okay, but we are going to have like a little bit of a work class this class. Yes. KP is not in the curriculum. No, it is AP only. KP is AP only. It's just those two from the previous one that were in there, just manipulating K, EQ. Yeah. Okay.